Okay, so in order to name compounds, the first thing we need to be able to do is name the ions themselves. And some of them are incredibly easy. Cations. The cations keep the name of the metal. And you write the word ion after it. So, Ca is calcium. Ca2 plus is the calcium ion. So the only thing you have to do is add the word ion after it. Pretty easy. Okay. Anions. Anions are going to be made by nonmetals. And we were looking at polyatomic ions. We saw that they often ended in ate or ite. Well, for the ones that come off the periodic table, we changed their ending to IDE. So Cl is chlorine. Chlorine's a nonmetal. It's on the right-hand side of the zigzag line. It's in group 7A, so to look like a noble gas, it would have to gain one electron. And when it gained that one electron, we wouldn't call it chlorine anymore. We would call it chloride, the chloride ion. So when you brush your teeth, you don't brush your teeth with fluorine, because fluorine's a poisonous gas. Instead, what's in your toothpaste is fluoride, because fluorine it'll take an electron from everything, including you and all the chemicals inside of you. That's why you don't want fluorine. Fluoride has already gained the electron, so it's not dangerous. Fluorine versus fluoride. Doesn't matter what the number is. Okay? So select the following with the correct names. Is A correct? Well, all you have to decide is it a metal or a non-metal? Well, K's a metal. It's on this side of the zigzag line. They're metals. We leave them alone, so it's called a potassium ion. That's correct. Oops. That's correct. Is B right? Well, F is a non-metal. It's a negative ion. Negative ions, we said we changed the ending to IDE, and that doesn't say IDE, it says INE. So B is incorrect. Is C correct? Well, GA is on the left-hand side of the zigzag line. It's a metal. And if it's a metal, we leave it alone. I don't want to change that ending. I want to call it the gallium ion. D, selenide ion. Well, Se is on the right-hand side of the zigzag line. It's a nonmetal. So, nonmetals, we change the ending. That's correct. What about Mg2 plus? Well, Mg is a metal, so one of the alkaline earth metals, right? So it's going to be, leave it alone, magnesium ion. And sulfide ion? Well, sulfur's a nonmetal, change the ending, it's okay. So when it asks you to write the names of the ions, all you have to decide is Do I change the ending or don't I? And that's it. Do I change the ending or don't I? Oh, and write the word ion. Yeah.
So if it's a non-metal, you change it to I. It doesn't matter if it's gaining or losing.
Oh no, it's not metal. It will always gain.
What about like bismuth?
Okay, bismuth is a metal. It's going to lose. But no, it's the zigzag line. It's the left-hand side. Bismuth is a metal. Now that gives us a way that we can talk about the different ones the different ions they can make, because the silicon ion means it's behaving like a metal and losing 4 electrons. The silicide ion means it's gained electrons. Does that make sense? That ending tells me whether it's a loser or a gainer. So it's not a new decision. It's the same decision, loser or gainer, metal or non-metal. Metals I leave alone, non-metals I change. Now to go the other way. Oh, actually, to put those ions together. When I want to write the formulas, we did a lot where you took the dots and you made the move. Okay. So that I can see that it would take 2 Ks for each O. There's a shorter way. Okay. The whole key to it is the charges have to add up to 0. So all you have to do is add the correct subscript to make them equal 0. Hey, so Na1 plus, and I knew sodium was going to make a 1 plus because it was in column 1A. O2 minus, I know O is going to make a 2 minus because it's in column 6A. Do those add up to 0? No. How could I make them add up to 0? Well, I would need 2 sodiums, right? So I put that 2 there. Well, it won't let me write there, so I put Na2O. And that adds up to 0, because 2 things that are 1 plus and 1 thing that's 2 minus equals 0. Okay, that? Subscript's got to make it equal 0. How about SR2 plus and Cl1 minus? I can tell the SR was 2 plus because it's in group 2A. The Cl's 1 minus because it's a halogen, gained 1 to look like a noble gas. Okay. Does it equal 0 the way it's written? No. So to make it equal 0, I'd have to I got 2 plus and 1 minus. That means I need more minus. So if I put a 2 there, that gives me 2 negatives. 2 negatives and 2 positives equals 0. So it's SrCl, 2. That adds up to 0. Okay. Now for the nastiest one I could give you. Fe3 plus and O2 minus. First of all, I would have to tell you that Fe makes the 3 plus. There's no way for you to know it, because Fe is in the middle of the transition metals. Remember, I always told you I would tell you what those were. Okay. O2 minus. I know that one because where it's at on the table, group 6A. Does it add up to 0 the way it is? Ah. Can't do that. So, Well, I don't have enough negative charge. So if I put a 2 next to that O, does that solve my problem? If I put a 2 there, I still have 3 positive, and then I have 4 negative. That doesn't work, does it? That doesn't work. It's 4 negative and 3 positive. That doesn't equal 0. But if I do that, then I need more positives. The next number I can get is a 2. Now it's 6 positives and 4 negatives. Still doesn't add up to 0. Make it a 3. That's 6 positives and 6 negatives. So the final one is going to be Fe2O3. Now there's a quicker way to do that. Okay? That would be, use word we don't like to hear, least common multiple. What's the least common multiple of 2 and 3? 6. So that's where they're going to run into each other, when there's 6 plus and 6 negative. It works on the ones above. What's the least common multiple of 1 and 2? 2. So that's why I needed 2 CLs. So I got my least common multiple. We didn't see it that way, but that's really what it was, least common multiple. Ooh, not allowed to use math words like least common multiple. Okay, there's actually an easier way. You take this 3 and you write it here. You take that 2 and you write it there. It works 95% of the time. The only time you have to worry about it is if it was something like SR 2 plus and C4 minus. Because if you put the 4 there and made that the 2, you have SR 4C2, but that's not the lowest ratio. I'd have to reduce that to SR2C1. That's the only way it doesn't work, is it doesn't give you the least common, right? Because the least common one here is 4. The least common one works every time. The crisscross 95% of the time. You just have to simplify, yeah, because our formula is the lowest ratio. Okay, notice I always put the metal first. Metal, that's the way they get written. Metal's first in the formula, metal's first in the name. So you'll see names like this. Potassium bromide. Now they're not even giving me the charge. How am I going to do that? Well, I can figure out the charge. Potassium's K. K's in group 1A. Group 1A always loses 1 electron. Group 1A always makes a 1 plus ion. We've answered questions like that already. They asked, what ions are going to form? Right? Bromide. IDE tells me it's negative. I should look over on the right-hand side of the table. It's bromine. Bromine is a halogen, group 7A. So it just has to gain 1 to look like a noble gas, which would make it a 1 minus. Does that add up to 0? Yeah, so we're done. KBr is potassium bromide. Beryllium fluoride. Hey, beryllium. Find it on the table. It's Be, and it's group 2A. It's an alkaline earth metal. What charge is group 2A going to form? It's going to lose 2 electrons and make it 2 plus. It looks like the noble gas before it. 1A always makes a 1 plus. 2A always makes a 2 plus. Fluoride. F, and F's a halogen, so it's going to be 1 minus. Does that add up to 0? No. What number will make it equal 0? A 2 next to fluorine. Because if I put that 2 down there, that's 2 negatives and 2 positives. Adds up to 0. Let me see how you can take just the name and figure out what the formula is. Okay. Now we named ions. Now how do you name the whole compound? Well, we just saw what the names were. It said beryllium fluoride, potassium bromide. I'm going to follow the rules when I write them, right? So what was in the names? Potassium and bromide. That was the names of the ions. It was made up of potassium ions and bromide ions. So the first word is the name of the cation. Metal. The name doesn't change. And the second word is the name of the anion. That's it. But remember, anions end in IDE. Negative ions end in IDE. So table salt is NaCl. That's its formula. What's its name? Well, Na is sodium, a metal. Cl is chlorine, but we changed the ending to chloride. So it's called sodium chloride. It's not ion anymore because it's neutral. Ion means it has a charge. So when it has a charge, it's called an ion. Without the charge, it's not called an ion anymore. Is that right? So let's try a few. Right, the name for MgF2. Well, Mg is magnesium. It's a metal, so I leave it alone. F is fluorine, but it's a non-metal, so I change it to fluoride. So MgF2 is magnesium fluoride. What about the 2? Nope. We don't include the number. Because chemists are lazy. They want to give you the bare information so that everybody gets the same answer. And it's easy to figure out. Metalloids depends on what they're attached to. Whether they're going to be, whether they're first or second. So if they're first, you leave it alone. If they're second, you change the ending. It's easy to figure out what the number is going to be. Why is that 2 there? That 2 there is because magnesium is 2 plus and fluoride is 1 minus. Those don't add up to 0. The only way they're going to add up to 0 is if I put a 2 there. And if it's that easy to figure out, it's not going to show up in the name. because we're lazy. We don't want to write any more than we have to. Magnesium fluoride tells me enough to know that it's MgF2 for everybody. Everybody's going to get the same formula. So what would you call Li2S? Well, Li is lithium. Wow, that far up. Lithium. And S is sulfur, so we change that to sulfide. So lithium sulfide. Ba3N2. Ba is barium. It's a metal, I leave it alone. H is nitrogen, non-metal. Actually, they go down to one syllable, so nitride. So the whole thing will be 2 syllables when you're done. That's what you get down to. You get 2 syllables in the name. If you want to know where to cut it off, so it's not oxygen, it's oxide. So you get down to just 2 syllables in that ide. Fluorine, fluoride. Sulfur, sulfide, nitrogen, nitride. Really, really tough? How can you change it to multiple choice? Which of these is the formula for potassium nitride? I was nice, I didn't put a P up there. Some of you are still putting P's for potassium. I saw that on the homework. Got your favorite picked? So I know it's K, I know it's N. I know K is in the first column. Always loses 1 electron, makes a 1 plus. N is in group 5A. For 5A to look like a noble gas, it would have to gain 3 electrons. So it's going to be 3 minus. Do those add up to 0? No, so I can do that crisscross. Or I can make it equal 0. Either way you look at it, I got to put a 3 there. Because that makes it equal 0. And it's the lowest ratio. So my answer was B. It's okay? What about Mg and O? So the hard part is figuring out the charges, and that's not that hard. It's just a matter of counting how far you have to go to get to a noble gas. So Mg, alkaline earth metal, the charge it's going to get, it's in the second column, so it's going to lose 2 electrons. It'll be 2 plus. The O, group 6A, to look like a noble gas, it would have to gain 2. It's 2 minus. Does that add up to 0? Yeah, it does. So I'm done. Or you could do the crisscross, get Mg2, O2. Can you reduce that to MgO? Make sense? Okay. So, I asked a lovely Bellware question today. How come an ionic compound takes both a metal and a nonmetal? I want to make an ionic compound, why does it take one of each? You drew pictures that said why. That arrow, right? We have to have something that loses to make a positive ion, and you have to have something that gains that makes a negative ion. Metals are losers, nonmetals are gainers. So it's always going to have a positive and a negative ion. Another way of saying that is it's always going to have a cation and an anion. And the way we're going to recognize that it has a cation and an anion is it's always going to have a metal and a nonmetal. So, which of the following could make an ionic compound? Mn and Mg, Ra and Ar, Rb and Rb, Na and N. Well, Mn and Mg, going to make an ionic compound? Mn is a metal, Mg is a metal. Got two losers, no gainer. Not going to happen. Ra and Ar. Ra is radium, a metal. Ar is argon, a nonmetal. But the answer is it's not going to happen. Why not? Because argon is a noble gas. It's not just, it's got to be a noble gas, it's got to be a nonmetal that wants to change. If you look like argon, you're going to stay looking like argon. You're not going to react. If you're already the king, you don't have to change to look like the king. Rb and Br. Rb, a metal. Pb, a metal. They're both metals, so not that one. Na, a nonmetal, and a nonmetal, Na a metal. One of each. It's going to be that. Doesn't matter what order they're in, I got to have one of each. Now, when I write the formula for that, I'm going to put the Na first and the N second, because metals always get written first. And Na is in group 1A, so it's going to make a 1 plus. Lose one electron to look like a noble gas. N is in group 5A. Gain 3 to look like a noble gas. So the correct formula would be Na3N. And now I actually want to look at some of the things you read about last night. It takes a while to set up, and I've got it set up today, so we're going to go off on a little tangent here, not be about naming. The homework's going to be all about naming, but I want to show this while I've got it set up. And so, along the homework, you asked that ionic solids were crystalline in structure. And crystalline structure means a regular repeating arrangement of the ions in the solid. That you have alternating positives and negatives. So that you know what kind of atom is going to go right, what kind of ion is going to go right there. There's no doubt about it, right? Now this pattern is simple because it's one of each. When you get to, you've got two of each, the patterns get a little bit more complicated, but there's always going to be a pattern. Always going to have a regular repeating pattern. And those are really strong bonds. Then to break those bonds would be to melt the ionic compound. Or if I want to get those atoms away from each other, I have to break those bonds. This structure is rigid. Ionic compounds are really hard. Ionic compounds have really high melting points. In order to melt it, you've got to take that positive charge away from those negative charges. So if you were to take sodium chloride, table salt, and put it in a pan by itself and turn on the gas and heat it up, it would be a race to see which would melt first, the salt inside the pan or the pan itself. And I think the pan loses, but you're going to melt the pan before you melt the salt. That means every time you have ever seen an ionic compound, it's been a solid. You've never seen a liquid or a gas that's an ionic compound. Now, we said it had a crystalline structure. Okay. This is how the atoms are arranged in sodium chloride. One of these is a sodium ion, and one of these is a chloride ion. Let's see if we can figure out which is which. You want to say the sodium is the big one and the chloride's the small one because they're in the same row and they get smaller as you go across. Except I don't have sodium atoms and chlorine atoms. I've got sodium ion. Sodium ion looks like neon. Chloride ion looks like argon. So the sodium is going to be much smaller than the chlorides. So the purple ones are the chlorides, and the yellow ones are the sodiums. And you can see it makes a regular repeating pattern. And they just happen to fit nicely together, so it ends up being a cube. Now, that's not just a bunch of atoms drawn together. Over here, I got a microscope hooked up to the TVs, and I'm just putting table salt on a slide, spreading it around. That's what table salt looks like when you magnify it. You notice something about the shape of these things? Oops, get some more light in there. Every light. You notice something about them? They're squares. They're cubes. Do you think somebody took the time to cut these all into microscopic little cubes? No, that's not how this happens. It's that pattern. They have to grow in the pattern. The pattern's a cube. So the pattern isn't always a cube, but they always have to make a pattern. So to show you that, I'm going to heat up a different chemical. This chemical is sodium thiosulfate. We don't do regular photo here anymore. We just do digital. So the only place I've ever seen it used is for developing black and white photographs. Okay? And I picked it because I can melt it. I looked for an ionic compound I could melt, and it was sodium thiosulfate. Notice it ends in 8, ATE. It's got a polyatomic ion in it. Polyatomic ion is going to be big, and it's going to be hard to make a nice pattern when you got big atoms. So I melted it. I Let's see if you can tell this is melted. See them floating around? Okay. Notice they're not cubes. But they're growing. Okay? Oh, automatically they thought that was a face. And notice when they grow, they don't grow randomly. They grow at a specific angle. Okay? So as they grow, this one has angles to it. Did I have to go out of my way to find a specific one that was going to grow at that angle? Actually, it doesn't matter which one I look at.